Good morning. Let's begin our class for today. So far, we've been talking a lot about first-order ordinary differential equations. And you've learned a couple of different techniques, the integration factor, separable, exactness. Today, we're going to start covering second-order ODEs. And the most important distinction to make with second-order ordinary differential equations is whether the equation is linear or nonlinear. If the equation is linear, the function you want appears in only linear forms, or its derivatives only appear in linear forms, then all of those equations can be solved analytically using different techniques that we'll start today. If it is nonlinear, then there are very few equations that can actually be solved analytically. And most nonlinear second-order ODEs need to be solved numerically using a computer. So you can't write down a nice little equation on a pen and paper for nonlinear differential equations. So that's why I drew a smiley face, because there's not much you can do to make analytical progress for nonlinear ODEs. So for the purposes of this class, we're going to teach you the basic tools that can be used to solve linear second-order ODEs. So from today onwards, we're going to focus only on linear second-order ODEs. So let's write down the generic form of a linear second-order ODE. Here is the general linear second-order ODE form. The function you want is the variable u, might be a velocity profile, temperature profile, concentration profile, and it's going to be a function only of x because we have an ordinary differential equation. And we have two coefficients, p of x in front of the first derivative and a q of x in front of the function itself. And on the right-hand side, we have a non-homogeneous forcing term given by g of x. Now, there are three cases to consider depending on the nature of p, q, and g. Depending on what those functions look like, the strategy that we'll use, the tools that we'll use to solve this equation will differ by a little bit. So let's write down the three cases for us to consider. So I've written here the three different cases depending on the nature of the coefficient p, q, and the right-hand side non-homogeneous term g. The easiest case is when p and q, which are coefficients on the left-hand side of the linear second-order ODE, are both equal to a constant, any constant, some constant that doesn't depend on the variable x. And lastly, the right-hand side, the non-homogeneous term, is equal to 0. The second case is when p and q are still equal to a constant, but your g, the right-hand side, the non-homogeneous term, can be any function of x. And lastly, the most challenging case, where p, q, and g, all of them, could be any arbitrary functions of x. Now let's consider the solution procedure, or the technique of solving these three different cases. Let's first start with the easiest case when p and q are constants and g is equal to 0. When your coefficients are constants, p and q are constants, and g is equal to 0, it turns out your solution procedure is one in which you'll solve for two linearly independent solutions, u1 and u2. And we'll cover how we're going to get the solutions for u1 and u2. But once you get those, you just add constants of integration c1 and c2 and add them together. So we've superimposed two different linearly independent solutions, and your overall solution u of x will just be the sum of those two solutions. We're going to cover this in detail, but this one is pretty easy. It will be the easiest solution to find for the linear second-order ODE in the context of these three different cases. Now let's consider the intermediate difficulty of when your p and q are constants, but your g of x can be any arbitrary function of x. All right, so in the intermediate case, when p and q are constants, g can be anything, then it kind of depends on the nature of g, your non-homogeneous right-hand side. If it is a, quote, simple function, then a lot of times we can just make a very good guess of what's called the particular solution. And you can add this particular solution to your overall function, and that's your solution. So you take your solution that you obtained from over here when g was 0, that's the first two terms, and the third term, you're going to tack in there a particular solution. Now, this isn't a strict rule. You can also find a particular solution even if your g of x is a more complicated function, but usually, if you have a straightforward function of x, this approach ends up working very trivially. Now, there are situations where your right-hand side g of x might be a weird function. I called it ugly, but some kind of weird function, like a step function, for example, or a pulse, a Dirac delta function, where your function value is 0, 0, 0, boom, at some point it spikes and goes back to 0. There are lots of mathematical functions that behave in very unique ways. And for those weird functions, there's a technique called Laplace transforms, where it's a very convenient way to handle unusual right-hand side terms of non-homogeneous deriving g of x. And I gotta say, the Laplace transform is one of the most remarkable mathematical formulations ever developed. And it's one of my favorite mathematical constructs and concepts ever. So I'm extremely excited to get into Laplace transform shortly. But before getting into that subject, let's do this case 3, when p, q, and g can be any arbitrary function. In that case, what do you do? The last case, when p, q, and g can be any arbitrary function, your best bet is a technique called the power series. Right here. Where what we're going to do is expand our solution, the solution you want, u as a function of x, as an infinite summation of polynomial functions of x. So we've raised x to the n power. We've put coefficients c sub n out in front that we can uniquely determine based on our equation, and sum them all together. So it's called the power series, which we will also cover in a little bit. So here we have it. For a generic linear second-order ODE, here are the 3 different cases that we're going to consider, and each case has a different technique for solving it. Linearly independent solutions, finding a particular solution, Laplace transform, power series. They're all different tools that you should all know as a scientist and engineer to know when and how to use it. But first, you have to know which one you should use. And these types of tree diagrams I really like because oftentimes you have so many different tools out there, it's convenient to know when you can use a particular tool. Okay, so first, let's focus on the easiest case over here when p and q are constants and the g function is equal to 0. So let's consider that case first. Let's first consider the case, the easiest case all the way on the left, where you have a constant p and q, which are equal to a and b. Again, just constant. A and b are just numbers, constant values that don't depend on x. And on the right-hand side, g of x is equal to 0. So this is a linear second-order ODE with constant coefficients. That's how you would describe the equation that we're about to solve. Now, I told you earlier that the equation here can just be written, the solution can be written, as just a sum of 2 functions, u1 and u2, each multiplied by a constant of integration, c1 and c2. So there's 3 questions that we would like to address right now. Question number 1, how are we going to obtain u1 and u2? I've been saying that those solutions exist, but we're going to show you the solution procedure to obtain u1 and u2. Second question is, how do you know that the solutions that you got are linearly independent solutions? Question 3, finally, how do you obtain c1 and c2? So let's get started with the first question. How do you even obtain the 2 solutions u1 and u2? So what you're about to learn in this class, and you've probably already seen already, is we solve differential equations by guessing. A lot of students think, oh, there must be something methodical, that there's some way of obtaining the solutions. There is, but it usually begins with a guess. Same with the integration factor. We just guessed that there's some mysterious function, capital F, that we can insert into the equation and somehow make it work. But it started with a guess. And that's true for differential equations across the board. We solve differential equations by guessing. We guess, strategically guess, and somehow make it work later. So we're going to do that here. We're going to guess a form of the solution u of x and see if that can work out somehow. And the particular guess we're going to make for this constant coefficient second order linear ODE has the following form. We're going to guess a solution, u of x is a solution you want, is equal to some constant a, capital A, times an exponential function raised to the lambda, whatever that is, times x. Our goal is to figure out what lambda is. A, as you will soon see, doesn't really matter. Now, we're going to make this guess, and we're going to plug this guess back into the original equation right there. So we need to take a couple of derivatives, plug it in to u double prime, u, and see what happens. So all I've done here is to substitute u of x into this constant coefficient differential equation. In the first term, you get two lambdas to come out because when you take two derivatives of u of x, our guess, with respect to x, lambdas just pop outside for a derivative of an exponential. The second term, we have only one lambda that comes out. This constant coefficient a just came straight down from the top equation. Finally, this last term, we plug in this equation, this form directly. The b just comes straight down. Now what you see is that a couple of terms cancel. Just like that, because our a, e to the lambda x is in every term on the left. On the right-hand side, it's equal to 0. And therefore, all we have left is a relationship between lambda, a, and b. Just like this. We get an equation that looks like this. It's an algebraic equation, a quadratic equation for our lambda, which are called roots. And we can actually solve this equation using the quadratic formula as a function of a and b. Again, a and b are known values. That's a part of your equation. You know what a and b are. They're numbers. 9, 5, pi over 2, square root of e to the 10. They're just numbers. So you can obtain what the value of lambda is based on solving this quadratic algebraic equation. And this equation is so famous that it has a name. It's called the characteristic equation for the roots lambda. This is called the characteristic equation. And if you obtain your values of lambda, you're going to get two roots, lambda 1 and lambda 2. Now, there's three different cases. Once again, differential equations are all about cases. There's three cases for us to consider depending on the nature of lambda 1 and lambda 2. Let's write down those three different cases. Three different cases depending on the value of lambda 1 and lambda 2. The first case is when your lambda 1 and lambda 2, that's my notation for lambda 1 and lambda 2, exist in the real number line. That's how you read that. So they're real numbers like 5, 10, -4. Those are real numbers. And they're distinct, meaning they're different roots. One might be 4, one might be -2. They're distinct roots. The second case is when they're still both real numbers, except they're double roots. So it's the same value. They're both -4, for example. Lambda 1 and lambda 2 equal to -4. It's a real number, but it's the same number. And lastly, when lambda 1 and lambda 2 exist in the complex plane. That's the C script with a line, vertical line in the middle. that means a complex number. So those numbers live along the complex number line, and that's case number 3. So for case 1, lambda 1 and lambda 2 are real and they're distinct. Then the solution is very easy. Your u1 is given by e to the lambda 1x. u2 is given by e to the lambda 2x. So there you have it. Going back to question 1 all the way up here, how to obtain u1 and u2, here it is. We already checked off question number 1. u1 and u2 are just exponential solutions raised to the roots of this algebraic equation. So if you can solve an algebra problem, you can solve this second order constant coefficient ODE. Now, when the roots are the same, it looks almost like these solutions with a very small minor modification. The first solution, u1, is actually the same. It's e to the lambda x, and now I'm no longer differentiating between lambda 1 and lambda 2. It's just lambda because it's the same root, identical root, e to the lambda x. The second solution, you need to put a factor of x out in front, right there. That is the only modification you need to make. Now, u1 and u2 are given by these two solutions. Again, question number 1, check. All right, so the last case, when lambda 1 and lambda 2 are complex numbers, right, you know that a quadratic equation like this could give you complex roots, right? Because the square root of b squared minus 4ac, that could be a complex number. And therefore, it's plausible that lambda 1 and lambda 2 give you complex roots. So what do you do in that case? When your roots are complex, it's going to take the form shown here. Lambda 1 and lambda 2 will be some real number alpha plus another real number beta times the imaginary unit I. So imaginary unit I is the square root of -1. And so lambda 1 will be alpha plus beta I, and lambda 2 will be alpha minus beta I. So it's going to have a real number alpha plus or minus imaginary number beta I. So your two solutions, u1 and u2, will just be each of those roots raised to the exponential. Exponential of alpha plus beta I, quantity times x, alpha minus beta I, quantity times x. So of course, exponentials add together, so we could just separate the real part with an imaginary part. Just like that. All I've done is to split the alpha plus beta I into a product of two exponentials, each raised to alpha x, or beta ix. On the bottom, we have alpha x, negative beta ix. Now, I wanted to do a quick aside on imaginary numbers and complex planes, because I think it's going to help us with simplifying those complex exponentials into functions that you've already have seen before. Let's do a quick aside. There's a very well-known relation called Euler's formula, and it tells us that when you have a complex exponential, e to the ix, then you can rewrite that as cosine x plus I sine x, where again, I is the imaginary unit, square root of -1. So you can break this down into a real part, cosine of x, plus an imaginary part, which has a height of magnitude sine x. You can now think of this as a vector, where the two vectors along this complex plane has a real component and an imaginary component. Now for this particular vector, the distance from the origin to a particular point along this complex plane has a real part magnitude, which in this case is given by cosine of x, and the height of that point along your y-axis, which is your imaginary axis, given by the magnitude sine x. So you can think of this as a vector along a complex plane of real and imaginary. Now, given this Euler's formula, we can rewrite the two exponentials that were in our u1 and u2, e to the beta ix and e to the negative beta ix. Let's rewrite those using Euler's expression. The two solutions that we had, u1 and u2, can be written as e to the alpha x, now using Euler's expression, cosine of beta x, plus I sine beta x, or minus I sine beta x for u2. And just a note here that we've used this relationship of an even and odd function for cosines and sines. So cosine of a negative quantity is just cosine of that quantity. It's an even function. Whereas sine negative beta x is negative sine beta x. It's an odd function. And therefore, this becomes positive cosine beta x, and there's a negative sign in here that pops out once you put a negative sign up here. It comes outside the sine function. Okay, so now with this in mind, let's consider the summation of the two functions u1 and u2. As I said earlier, the total solution is the sum of two functions u1 and u2 multiplied by a constant of integration c1 and c2. So what I've done here is to plug in u1 into here, u2 into there, and I rearranged some terms here and there. So first, I pulled out the e to the alpha x that's common in both of these functions. So it will just pop outside of the brackets. And secondly, what I've done is to factor out the cosines and the sines from each of these solutions. So from u1, I'm going to have c1 times exponential alpha x, which is already pulled outside. So we're just going to get c1. And from the second u2, we're going to get a c2. Okay, just factored out c1 and c2, multiplied against cosine beta x. Same thing for the sine. We're going to get c1 minus c2 because there's a negative sign in front of the negative I, and therefore we're going to get c1 minus c2 times I times sine of beta x. Now, at this stage, we're going to redefine the constants into a new constant because c1 and c2 are both just numbers. They're just constants. So I can define a new constant called c1 plus c2 as c1 prime, and this other constant, c1 minus c2 times I, as another constant, just called c2 prime. So now, cleaning things up, let's rewrite our total solution. Just like that. So we have c1 prime e to the alpha x cosine beta x plus c2 prime e to the alpha x sine beta x. So apparently, I can also have two separate solutions, u1 and u2, where everything here is one of our solutions, u1 of x, and the other one is u2. So we have an alternative form of u1 and u2 where we could just write down whenever we have a complex root, lambda 1 and lambda 2, along the complex plane. Now, this concludes our aside on the complex roots and Euler's formula, but I think this Euler's formula is just a pretty remarkable thing. And actually, complex numbers in general are just really wild to think about. For example, we could use Euler's formula to do some pretty crazy algebra. Let me ask you a question. You guys all know that the imaginary unit I is equal to -1. Well, let me ask you, what about the square root of the imaginary unit I? Do you know what this is? So that is square root of -1. Oh my gosh. This is just making me nauseous just looking at this. Oh, so many brackets, -1. It's just kind of nasty and nauseous to think about. But Euler's formula comes to your rescue. So let's think about, is there a way to rewrite I in a different way? Of course there is. Because if you look over here, you have e to the ix is equal to cosine x plus I sine x. What this means is that if there's some way to make cosine go to 0 and sine go to 1, then e to the ix would be equal to I. right? And it's pretty easy to think about what value of x is that true for? Pi over 2. When x is pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is 1. Therefore, apparently, we can just rewrite I as e to the I pi over 2. This is a true statement. It's identical representation. Well, representation is different, but it's an identical number based on Euler's formula. Now, the thing that we want to obtain is the square root of this quantity, which is just raised to the half power, right? Exponentials could just be raised, and it's the product of the exponentials. So this is true. I've just taken 1/2 power of both. That's perfectly fine to do. So apparently, the square root of I is just e to the I pi over 4. But then, e to the I pi over 4, using Euler's expression, is pretty easy to determine. And sine of pi over 4 is also root 2 over 2. It's just along the 45 degrees. It's both root 2 over 2. So apparently, which is crazy about this, is that square root of I is nothing more than root 2 over 2, 1 plus I. This is crazy. I don't care what background of math you come from, but the square root of the square root of -1 is root 2 over 2, 1 plus I. I think this is crazy. I just think complex numbers are the wildest thing, and it's actually very important in science and engineering. So there's an entire class on complex analysis that teaches you how to take integrals along the complex plane. You can take integrals along this real and imaginary plane and be able to solve really crazy things, like walking around a mountain tells you how tall that mountain is. That's a contour integral along the complex plane, and it just is the wildest thing. And branch cuts, how you can go through singularities, and you can do things in calculus that seem to defy norms in the real plane very easily in the complex plane. So you can already tell based on this Euler's formula that there are spooky things that happen along the complex plane. And this is just a very short introduction into the crazy things that can happen in the imaginary axis and plane. In any case, that was a short aside, but the really important thing I wanted to tell you was that when you have a complex root for the characteristic equation, U1 and U2, these are the solutions that we should write down. Let's return to the previous diagram that we had with the 3 different cases. All right, as you just saw in the aside, you can do some massaging of the 2 complex exponentials, e to the beta ix and e to the negative beta ix solutions, rework some terms together, such that we can write our 2 solutions, u1 and u2, in the form that I've written down here. So we have 2 complex roots, lambda 1 and lambda 2. Then your roots can be expressed as alpha plus or minus beta I, and your 2 solutions that you should write down are u1 is e to the alpha x cosine beta x, and u2, the other solution, is e to the alpha x beta sine beta x. So there you have it. For constant coefficient linear second order ODEs, you write down your characteristic equations after making a guess of an exponential form. You have 3 different cases of what lambda 1 and lambda 2, your roots of your characteristic equations, can be. And depending on the nature of those values, you have 3 different possible solutions that are solutions to your equation. Now, at this stage, we've completely answered question number 1 all the way up here. And let's now move to question number 2. How do you know when u1 and u2 of these 3 different cases are linearly independent with respect to each other? Let's talk about that next. You now know how to obtain two solutions to the second-order constant coefficient linear ODE. Now, I'd like to return to the original three questions that we wrote on the upper right-hand side of the board, which was, first, how do you obtain solutions U1 and U2? Second question, how do you know that those two solutions are linearly independent of each other? And question 3, which is how do you obtain the constants of integration? Let's tackle question 2, which is how do you know that the two solutions that we just solved for, U1 and U2, are actually linearly independent? In fact, let's take a step back. What does linearly independence even mean for a function? Let's first define what we mean when two functions are linearly independent of each other. If and only if this function w, which is the determinant of your two solutions, u1 and u2, and their derivatives, u1 prime and u2 prime, if this function is not equal to 0 for all x, then you are guaranteed that the two solutions that you found, u1 and u2, are linearly independent of each other. Now, you probably heard about linear independence in the context of vectors and matrices. When you first took your linear algebra class, you probably learned how a matrix can be linearly independent, or how the rows or columns of a matrix can be linearly independent of each other. In the context of linear algebra, here's what you learned. When you have two vectors, v1 and v2, those vectors are linearly independent if these two vectors space span the whole, in this case, two-dimensional plane, both along the x and the y. But if you were to have a v1 vector be equal to, for example, 1, 0, which would just be a vector that lies along the x-axis, and your v2 just be twice that of v1, then these two vectors would both just lie along your x-axis. So no matter what linear combination that you took of these two vectors, any combination of constants of c1 and c2 will never allow you to space span the whole 2D xy plane. And the way you get them to space span the whole space in this particular case is if one of your vectors has an element in the second dimension along the y direction. The moment you have any kind of y dimension in one of your vectors, you can combine those two vectors to create any point along your entire 2D plane. So a lot of times what you have learned in your linear algebra class is to put these two vectors in the form of a matrix. So you take these two vectors, put them into a matrix, and you get entries that would fall along each of your vectors, wherever it fell along a particular vector location. And if they space spanned, that means that your columns were linearly independent of each other. That's what you proved. And you took the determinant and you proved that you had two eigenvalues, et cetera, right? That's how you kind of learned about linear independence in linear algebra, in vectors and matrices. Turns out that functions could also have a similar analogy to what you learned in linear algebra. Two functions need to be able to space span the whole function space. So in this particular case, if, for example, your u1 function were to be some function, let's just say x, and if your second function was 5x, these two functions are not linearly independent of each other because u2 is just 5 times u1. It's just a simple multiple product of the function number 1. Therefore, these two functions will not allow you to space span the entire function set. And therefore, in analogy with linear algebra and vectors and matrices, you do the same thing. You take two functions, u1 and u2, take their derivatives, and you check the determinant. And this function right here is called the Wronskian. It's got a really cool name. It's called the Wronskian. So if we were to just determine what this function looks like, let's multiply this matrix out. And I'm also going to erase this example because this is a bad example of two functions that are linearly dependent on each other. So we don't want to use this example. So here it is. I just literally took the determinant of this matrix. It just becomes u1, u2 prime minus u2, u1 prime is not equal to 0. If this is true for all x, you are guaranteed that these two functions are linearly independent of each other. So then, let's consider our two solutions that we got from our solution guess with the exponentials. u1 is equal to the exponential of lambda 1x, u2 is equal to the exponential of lambda 2x. Let's plug it in to this expression of the Wronskian and see what we get. For the particular case that we're considering, we want to check if our two solutions that we obtained, u1 and u2, up here, are linearly independent with respect to each other. So I've taken their derivative with respect to x. So now these are the four entries in blue that we need to fill out the determinant with. So our Wronskian is determined as a determinant. So we plug in those four terms into the Wronskian. And if you factor out lambda 1 minus lambda 2, you get the following form. You can see this pretty easily. You just multiply this term over here on the upper left with the bottom right. That's the first term. And you subtract out the other diagonal, this term. And so you can see that there's a common factor of lambda, e to the lambda 1x plus lambda 2x. Pull that out, and out comes lambda 2 minus lambda 1. Now, the rule says if this form, right, the Wronskian, is not equal to 0 for all x, then we're guaranteed that u1 and u2 are linearly independent. Now, an exponential function cannot be 0. For all x, for any value of lambda 1 and lambda 2, this exponential can never be 0. So we're fine on the second term. The main question is this first term in the parenthesis, lambda 2 minus lambda 1. Now, if lambda 1 and lambda 2 are the same, then this would be equal to 0. But if they're not, then we are guaranteed that u1 and u2 are linearly independent with respect to each other, according to this definition. And going back to linear algebra, that would imply that these two functions, just like vectors that space span the whole column set or the row set, we're guaranteed that those two functions span the whole solution set. Okay, so let's write that down. Okay, I've just written that down. So if lambda 2 and lambda 1 are not equal to each other, we are guaranteed that the Wronskian is never equal to 0, and therefore, if we have two distinct eigenvalues, lambda 1 and lambda 2 are distinct, not the same, then we're guaranteed that these two solutions that we wrote down here are linearly independent with respect to each other. Now, remember those three cases? When you wrote down the characteristic equation, there was case 1, lambda 1 and lambda 2 real, distinct. Case 2, lambda 2 and lambda 1 same, real numbers. Case 3, lambda 2 and lambda 1 distinct, complex, imaginary numbers. Now, case 1 and case 3, this applies because they're distinct and they're okay. So you're guaranteed that we have the right solutions. For case 2, that was the unique one where lambda 2 and lambda 1 were the same. And if you recall, the second solution was not e to the lambda x. There was a factor of x that we pulled outside. It was x times e to the lambda x. And let's see why we had to do that. It has to directly do with this linear independence and the Wronskian. So let's consider that case 2 when lambda 2 and lambda 1 are equal to each other. What happens in that case? Let's consider the special case where this doesn't seem to apply, when lambda 1 and lambda 2 are real and they're the same eigenvalue, equal to lambda. We said that in that particular case, the two solutions should be e to the lambda x and x times e to the lambda x. So there's a factor of x outside, right there, that we wrote down earlier. And here's the reason why. When you write the derivative and the derivative of u1 and u2, the derivative of u2, you have to use the product rule. You keep x constant. So there's a lambda x, e to lambda x that comes outside. You keep the other one constant. There's a factor of 1 that pops outside. So this is just a simple derivative of the function u2. Now, if we go back to the definition of the Wronskian, up here, and plug in the terms here into the Wronskian, see what we get right here. Okay, I've just literally plugged in u1 times u2 prime. That's the first term over here on the left. That just simply gives you e to the 2 lambda x because the exponentials add. And we get the 1 plus lambda x to just fall straight through. And then second term is minus u2 times u1 prime, u2 times u1 prime. And you simply get lambda times x, e to the 2 lambda x. And you can see that one of the two terms cancel. Therefore, all that you're left with is just this term right here, e to the 2 lambda x. And for all general x, this can never be equal to 0. Therefore, according to this theorem, we conclude that because the Wronskian is not equal to 0 for all values of x, these two solutions right here, that one and that one, are indeed linearly independent with respect to each other. That's why the second case, when lambda 1 and lambda 2 were equal to the same eigenvalue, they were real numbers, we had to add this extra factor of x outside. Because if you didn't, we would be right back here. And if lambda 1 and lambda 2 were the same, this would be equal to 0. And we have not found our two linearly independent solutions. All right. So that's all I wanted to talk about in terms of linearly independent solutions and functions. We now know that all three cases of lambda 1 and lambda 2 are linearly independent. And we now know how to get the two solutions u1 and u2. So we've answered 2 out of the 3 questions we wanted to set out today. How do you get solutions u1 and u2? How do you know that they're linearly independent? Let's do a couple of example problems to wrap up and do a summary of what we learned so far. Let's do a couple of quick examples. I've just written 3 examples up here that we like to solve using the techniques that we've learned so far. So let's do example number 1. U double prime plus 5u plus 6 equals 0. So once again, we guess differential equations, right? That's how we solve them. So let's guess we guess the solution for differential equations. Let's guess the form of the solution. We guess the form of an exponential. We plug this solution back into our equation. We get this. The exponential here can never be equal to 0, which means that the terms inside the parenthesis must add to be 0. We could just factor out common terms here. Therefore, we conclude, based on the characteristic equation, that the two eigenvalues are -3 and -2. And because the roots are distinct and they're real, that's the first case where the solutions are simply raised to each of these exponents. Just like that. All right, let's move on to the second example. Same thing. This time I'm just going to jump right to the characteristic equation. We could again factor out, just like that. And therefore, this is a particular case where lambda 1 is equal to -3, but lambda 2 is also equal to -3 because we have a double root. And because we have a double root, our two independent solutions are the following. Just like that. First one is just e to the -3x. The second one, you need a factor of x outside because once again, that's what's needed to make these solutions linearly independent, a space span the whole function set. Lastly, you can kind of probably guess what's coming for this example, but let's just do it anyway. Again, skipping to the characteristic equation. Just like that. And therefore, we're going to have to use the quadratic equation in this case. I've just done the quadratic equation here. -b plus or minus b squared minus 4ac divided by 2a. And inside this square root, I have 4 minus 20. So that's -16 inside the radical, which means I'm going to have a 4i, where I is the imaginary number on the upper right-hand side here, divided by 2 simply gives plus or minus 2i. And therefore, the two roots, lambda 1 and lambda 2, are -1 plus or minus 2i. Once again, like I said, with complex numbers, you're always going to get them in pairs. Plus imaginary number, minus imaginary number. And so this is case 3, when lambda 1 and lambda 2 are complex and they're distinct. So the solution, as we showed you with the Euler's formula, can be written down like the following. Just like that. So e to the negative x comes from the first term, remember the alpha x that came outside, times this is the two solutions cosine 2x, that's the beta term, and C2 sine 2x. So there you have it. It's pretty straightforward. You just find your characteristic equation. You solve an algebra problem to find your roots, lambda 1, lambda 2. Based on the nature of lambda 1, lambda 2, you write down your three different types of solutions. That's it. And at this stage, you know everything you need to know about solving homogeneous equations. In other words, when the right-hand side, the non-homogeneous term, is not present in the second-order constant coefficient linear second-order ODE. Now let's consider when you have a g of x. How do you find what's called the particular solution in addition to the homogeneous solution that you have here when, in this case, the right-hand side were all equal to 0? When they're not equal to 0, how do you find that extra solution? We're going to cover that next. Remember that tree diagram that I wrote a long, long time ago? You've probably forgotten by now. I wrote it by hand, but I have produced a digital version of that for your convenience. So we're considering linear second-order ODEs written up here. Okay, u double prime plus some coefficient p times u prime plus another coefficient q times u is equal to the right-hand side, the non-homogeneous term g, as some function of x. Now, so far, we have just considered this left-hand branch. When p and q are constant coefficients, so just numbers in front of the u prime and u, and when g was equal to 0. Those are called homogeneous solutions, right? u1 and u2 were pretty easy to solve. You just found your characteristic equation, you found lambda 1 and lambda 2, and you obtain your homogeneous solution u sub h as a function of x is equal to c1 u1 plus c2 u2. Easy, piece of cake. You've probably already seen this once before, but it's always good to see it again and to review some of these materials. Now, let's consider this second case, right down the middle, where p and q are still constants, but now g, this non-homogeneous right-hand side term, can be any function. And in particular, we broke it down into two separate categories. One is when I said g of x is, quote, simple. We'll let you know what you mean by simple. If it's in this particular category, then our overall solution u of x is simply a sum of the solution you already got, right? U sub h is this first term over here. That's the function that you already know how to get. But you need to add to that an additional term over here on the right-hand side, u sub p, for particular solution. And you add those two solutions together, and your overall function u is a solution to this middle case. Basically, this u sub p term, the particular solution, handles the right-hand side term g of x. It takes care of that fully for you. Now, when g of x is not simple, weird or unusual function, like a Dirac delta function or a step function, we're going to talk about that in a little bit, then there's a much more elegant technique called the Laplace transform technique that we're going to cover in this class in a couple of lectures. Now, the hardest case over on the right-hand side, when p, q, and g can be any arbitrary function of x, then over there, we can't use this easy approach that you see on the left-hand side. We need to use a technique called the power series, where is an infinite summation of some coefficient c sub n times a polynomial function x to the n power. We're going to cover that right after this chapter in this lecture right here. But for today, let's still consider this middle case, when p, q are constants and g of x can be anything. And in particular, let's cover the case where it is what I'm going to call a simple function, such that you can just take your homogeneous solution that you already have, add to that a particular solution, and you're all done. So you already know how to solve the homogeneous solution. We're going to today focus on how to solve the particular solution u sub p. And in general, there's kind of two techniques in solving the particular solution. You've probably, again, heard of them or have done them yourself once in the past, but it's, again, good to review. So the two common methods, one of them is called method of undetermined coefficients, and the second one is called variation of parameters. These two techniques, method of undetermined coefficients and variation of parameters, those are the two common techniques that are used to find this particular solution u sub p. Now, the method of undetermined coefficient, if it works, is the easier method. And the overall theme of this approach is guess it and fix it. We'll see what we mean by that. What do you mean by guess it and fix it? You'll see in a little bit. The variation of parameters is an approach that is a little bit harder, but it always works. It's guaranteed to work, but the calculation is more cumbersome. Okay, so variation of parameters, a little bit more cumbersome to do, but it always works. And the basic premise of variation of parameters is you take your two known solutions, u1 and u2, you use those solutions to build up your particular solution. So if you can solve the homogeneous solution over here on the left, you are guaranteed to be able to solve for your particular solution. Well, let's first consider the case A, or the approach A, method of undetermined coefficients, because if that one works, you should always use that one because that is much easier, less cumbersome than the second approach. So let's cover method of undetermined coefficients. Now, here I've written the generic form of constant coefficient. So now I've replaced p and q by the constants a and b. Now we have a right-hand side, g of x, not 0 anymore. So you already know how to solve the homogeneous part. So we write down the full solution, u of x, as the homogeneous solution, u sub h, that you already know how to find based on the characteristic equation, lambda 1, lambda 2, you obtain your u sub h. In the second term, you add to that a particular solution, which is what we're trying to find right now. How do you find u sub p? Now, it turns out that if your right-hand side here, g of x, written in green, takes on very specific terms, then you can guess the form of your particular solution, u sub p, and make it work. So the theme is you make a good guess, and you find what the constants are, you massage it here and there, you make the constants work out such that it captures the right particular solution. So there's three classes that are actually very common in science and engineering to have a right-hand side, g of x, that takes the form of three different types or classes of functions. So let's write them down. I'm going to write down the g of x on the left-hand side, and on the right, I'm going to write down what form of the particular solution you should guess to make it work later. So the first class of common functions that you'll find on the right-hand side is a polynomial function of degree n. For example, x to the second power, x to the 10th power, polynomial functions. And in that case, what you should guess depends on the particular value of your eigenvalues, lambda 1 and lambda 2. So if you found your homogeneous solutions, lambda 1 and lambda 2, and neither of your eigenvalues and your roots were equal to 0. In other words, lambda 1 was not equal to 0 and lambda 2 were not equal to 0. Neither equal to 0. Then the particular solution that you should guess to make it all work is also a polynomial form. So u sub p would be equal to a naught plus a1x plus a2x squared all the way to a sub n x to the n power. And you go up to the n power that corresponds to the degree n of your function g of x. So for example, if your g of x was x cubed, then you would need to keep a naught, a1, a2, a3, x cubed. So you keep those four terms for your particular solution. Okay? And we'll cover how do you find your a naught, a1, a2, all the way to an in a little bit. But for now, let's just keep moving on and just assume that you can find that. We'll show you how later. Another case is if your lambda 1 and lambda 2, either one were equal to 0. If lambda 1 or lambda 2 were equal to 0, then what you do is you just take the solution that we had earlier, a naught all the way to a sub n x to the n. You take the whole function, multiply it by another factor of x. It again has to do with the roots. Okay? So now you have to multiply by a factor of x for the whole thing, and that's what you would guess. And again, we've obtained our a0 through an, and I'll show you that technique in a little bit. Last case is if a lambda 1 and lambda 2 were both equal to 0. So case B is if one of them were equal to 0, but not all of them. Case C is if all of them, in other words, both eigenvalues, lambda 1 and lambda 2, were both equal to 0. Then all you need to do is put another factor of x, so x squared times the whole polynomial, and that solution would capture a particular solution correctly. That would capture this right-hand side term g of x. All right. So the second class of functions that are very commonly seen in science and engineering that also works with method of undetermined coefficients are exponentials. So if your right-hand side g of x already has the form of an exponential, then there are, again, certain cases where you should guess a particular form of the particular solution. So the first case, if your eigenvalue lambda 1 and lambda 2, neither of them are equal to this constant k sitting outside in front. Okay, I don't want you to be confused by all the exponentials. So the homogeneous solution has exponential solutions. Those have roots lambda 1 and lambda 2 raised to the exponential powers. If your non-homogeneous term g of x also has the form of an exponential, you can compare the roots lambda 1 and lambda 2 with the prefactor inside your exponential for the g of x term. So if neither of them are equal to k, then you just simply guess another form of an exponential, e to the kx, with a prefactor a. We'll find a in a little bit. If lambda 1 or lambda 2 is actually equal to the exponential prefactor inside the g of x, then you just need a factor of x out in front. And if lambda 1 and lambda 2 are both equal to k, it's a double root, then you need this x squared factor out in front. Okay? Lastly, if your right-hand side g of x has the form of sines or cosines, then here's the form of the solution you should guess. Case A is when lambda 1 and lambda 2, neither of them are equal to I, the imaginary unit, times k. In that case, your particular solution just takes a linear combination of cosine and sine, kx. Constants that we'll find, a and b. Second case, if lambda 1 or lambda 2 were equal to ik, in that case, you need a factor of x out in front. Some of you might be wondering, what about case 3, or case C in this case? There is no case C. When you have exponential roots like this, you can never have it equal to ik. Okay? You can never have a double root like that. Okay? So in this particular case, these are the only two situations you need to consider for your particular solution. So now all you need to do is, let's say if your g of x was a sum of many of these categories. For example, you had g of x that was equal to x squared plus a cosine kx. Then you would add together these polynomials to x squared plus this particular solution together. So you would just superimpose the different particular solutions together, add them together, and that would be your total particular solution that would cover both the x squared right-hand side plus the cosine kx term. Okay? We'll do a couple of examples and you'll see how all of this comes together, but also you'll see how we're going to find the constants. A sub n's, capital A and B. So let's do a couple of examples to see how this all comes together. But before that, I recommend you take a screenshot of this. This is a perfect screenshot time. I'll actually duck and get out of the frame so that I don't contaminate this beautiful screenshot with myself. So screenshot time. Okay, I hope you got it. Let's do a couple of examples. Let's do this example. U double prime plus u is equal to x squared. Now, let's just follow the steps. This is constant coefficient, second order, linear ODE, non-homogeneous. So it's right along the middle branch of that tree that I showed you earlier. Okay? So following the steps, we add a homogeneous solution and the particular solution. So let's first solve the homogeneous solution. So the total solution is equal to the homogeneous solution plus the particular solution. The homogeneous equation is simply the following. The characteristic equation is lambda squared plus 1 is equal to 0. Therefore, the roots of our characteristic equation have imaginary roots. It would just simply be I and negative I. And therefore, our solution is just sine and cosine. Just like that. So we have our homogeneous solution, C1 cosine x, C2 sine x. That plugs directly into our homogeneous solution. Now we need the particular solution. We just covered how to do that. So in this particular case, we have a polynomial g of x with degree equal to 2. So according to that table that you just took a screenshot of, we should guess a polynomial form up to degree 2. So our particular solution, according to that table, is simply going to be a naught plus a1x plus a2x squared, because we have a polynomial of degree 2 for the right-hand side g of x. Therefore, all we need to do is plug this solution into our differential equation and match terms to make everything work out. So we need to obtain a second derivative from our guess to plug into the equations. Let's take two derivatives of this solution with respect to x. Just like that. So now all we need to do is to plug in u double prime plus u is equal to x squared. So all I've done here is to take up double prime, because the original equation has a double prime. So it's up double prime, that's 2 times a2, plus up, because our original function here, our equation just has a u. This is all of just up up here, is equal to the original right-hand side, which is equal to x squared. Now, it's just a puzzle game where you match like terms and make the coefficients all work out. So on the right-hand side, we have an x squared, and the prefactor is 1, right? It's 1 times x squared. If you scan the left-hand side, you have one term right there that is a2 times x squared. There's no other terms on the left-hand side equal to x squared. And therefore, the only possible way in which we can make this work is if a2 equals 1. If a2 equals 1, we're all good to go, because now we've matched the like terms, because we need to make this equality all work out. We need to make the left-hand side equal the right-hand side. That's what the ODE is. Left-hand side must equal the right-hand side. So on the left-hand side, we have this a1x term. Over here, there's no linear term. It's 0 times x. Therefore, a1 better be equal to 0, because if it's not, that would mean that we have a linear term on the left-hand side that doesn't equal the linear term on the right-hand side. So we need to basically kill off this linear term on the left-hand side such that it equals the terms on the right-hand side. Same thing with the constant. Over here, we basically have nothing. We have 0 on the left-hand side, which is a constant, right? It's just x squared. 0 times x plus 0, which means that everything here, all of that, which on the left-hand side corresponds to constants, those must be equal to 0. Okay? But we already know what a2 is. a2 is equal to 1. Therefore, we just have that a0 is equal to negative 2. So there we have it. We found a naught, a1, a2, which is a0, a1, a2. Once we have those three constants, we're done. So apparently, our particular solution is nothing more than the following. I've written here on the upper right corner, negative 2 plus x squared, because that is a particular solution such that if I were to plug in negative 2 plus x squared into this differential equation, the equality will be preserved. So apparently, I have a homogeneous solution which satisfies this equation equal to 0 on the right-hand side, and one particular solution that satisfies the right-hand side. If I add those two solutions together, I get the most general solution. All I've done here is to take our total solution, wrote down the homogeneous solution C1 cosine x plus C2 sine x, which you found earlier, added to that the solution from the upper right-hand side over here, boom, right here to the total solution. Therefore, this is the total solution of this differential equation, including the non-homogeneous term g of x, which is totally covered by this particular solution. Now, one important point about the final step, which is the third question, the grand question I wanted to answer in this lecture, which was, how do you now obtain constants of integration C1 and C2? To obtain those constants, you need boundary conditions or initial conditions. Because this is a second order ordinary differential equation, you would need two conditions. You'd either need a position and a velocity, so those are two initial conditions, or you need something like a boundary condition at x equal to 0, x equal to L. You need basically two conditions that will allow you to determine C1 and C2. The important point is you need to evaluate those boundary conditions and initial conditions on the total solution here, including the particular solution. You can't just take the homogeneous solution and expect that to give you the constants of integration with the boundary condition, initial condition. Apply the constraints in the boundary condition, initial condition at the very end once you've obtained your entire solution, including your particular solution. A lot of students make a mistake on this where they'll evaluate the constants halfway through without solving for the particular solution. Just do the entire problem all the way through and then evaluate your constants C1 and C2. And after that, that's it. So method of undetermined coefficients is very effective if your right-hand side, g of x, takes on a polynomial, exponential, or sines and cosines. Let's move on to variation of parameters, which is what you would do if the right-hand side is not a convenient function. If method of undetermined coefficient fails, then there's another technique that is surely going to work, although the calculation is a little bit more cumbersome. And it's called variation of parameters. And the basic premise is that we already just found our homogeneous solutions U1 and U2. Those are the homogeneous solutions. We're going to use those two solutions to build up a particular solution U of p. Now, it also starts with the premise of a guess for a particular solution based on linear combinations of U1, U2. They're not actually linear combinations. I should correct myself. They're combinations of U1 and U2. Let's write down the basic form of the variation of parameter solution to U sub p. It looks something like this. So we're going to guess a form of the particular solution as a combination of your homogeneous solutions. So you know what U1, U2 are, but we're going to introduce another pair of functions that we don't know, v1 of x and v2 of x. And the basic idea is we're going to take combinations of U1, multiply it with the right amount of v1 of x, and U2, multiply it by the right amount of v2x, add them together such that this composite equation, UP, solves the right-hand side g of x as the particular solution. Now, we've made this guess, and as usual, we're going to take this guess, substitute it into the original form of the ODE, u double prime plus a times u1 plus b times u is equal to g of x. Now, when you do that, there's two conditions or constraints that you have to use in order to obtain what v1 and v2 are. Let me write down those constraints. Okay, like I said, we're going to take this form of u sub p that we're going to guess, substitute it back into the full ODE, including the right-hand side g of x. Now, you're going to get a long and ugly mess of an equation that I'm not going to write down, but we're going to have to impose one condition, which is that the derivative of your v functions multiplied by u1 and u2, this must be equal to 0. It's a condition that we are imposing on top of this guess. And then when you do some simplification, your original ODE will whittle down to this equation right here on the bottom. You're going to obtain this equation. The derivatives of v1, u1, v2, u2 must be equal to g sub x. This is the equation that's required for this guessed form of the solution to satisfy the ordinary differential equation. Now at this stage, you can see that we have two equations, this one that we've imposed and the one that we obtained, with two unknowns, v1 and v2. So we can solve two equations with two unknowns. We have two equations, the one that we imposed, the one that we obtained from the ODE. We have two unknowns, v1 and v2. Now, after doing a lot of algebra, you obtain the following forms for v1 and v2. So after doing a lot of algebra, what you find is the following two equations for v1 and v2. Up here, we have negative integral of u2, the second homogeneous solution, times g of x, the non-homogeneous term, divided by the Wronskian, which is the determinant of your two solutions, your homogeneous solution u1 and u2. And v2 is the integral of your other homogeneous solution, u1 of x, multiplied with your particular the non-homogeneous term g of x, divided by Wronskian, integrated over dx. Now you perform these integrals, you plug it into this guess for your particular solution, and that's it. So as I said, it's more complicated than method of undetermined coefficients, but the nice thing about variation of parameters is that it is guaranteed to work. It always works because, think about it, you obtained your homogeneous solutions u1, u2. You know what u1, u2 are. And you know, obviously, what your g is, because that's the non-homogeneous term that's given to you in the ODE. And w, of course, you can also obtain from your homogeneous solution. And that means that v1 and v2 can uniquely be determined if you know what u1 and u2 are. So if you can get a homogeneous solution, you are guaranteed to get v1 and v2, and in turn, you are guaranteed to be able to build up a particular solution. And the nice thing about variation of parameters is that it works even for non-constant coefficient ODEs. So if you have p of x, q of x, which are some function of x, the coefficients in your ODE, variation of parameters will still work. Okay, so I think of variation of parameters as the sure shot way that will always work. So if method of undetermined coefficient fails, if all else fails, variation of parameters will always rescue us and be able to uniquely determine the particular solution. Let me just write that down. All right, variation of parameters always works, even for non-constant coefficient ODEs. And if you can get u1 and u2, the homogeneous solutions, you are guaranteed to be able to obtain your particular solution. So that's it, guys. I know this was a long, long lecture, but now you need to, you can solve all of these constant coefficient problems. You can get the homogeneous solution. You know that they're linearly independent. You can use one of the two techniques to obtain the particular solution. So second order linear constant coefficient homogeneous and non-homogeneous ODEs, you can now entirely solve. With that, let's end today. I hope you have a nice rest of the day. I will see you next time.